Today we are going to see the most important chapter which will give you ECPC marks, that is coordination compounds. This chapter is the most easiest chapter of your 11th and 12th. Okay, you are going to watch this video till the end. After that you can solve your problems of your own. No more doubts, nothing will be left unread. Okay, let's get started with the coordination compounds. Coordination compounds, why we are calling it like that? Because they are bonded through coordinate bond. What is that? Which means both the electrons are shared by the same ion or a compound or a molecule. Okay, the sharing will happen, but both the electrons from the same side. That is what the coordinate bond is. So point to be noted or important terms in coordination compound chapter is that the coordination complex will look like this. There will be a central metal ion. Here we are having cobalt, and then there will be a ligand which is providing the electron to the central metal ion. That's why we are representing it by the arrow mark. Okay, from where the electrons are going. Here the ligand is NH3, and then the sphere which is having a square bracket. So what is inside that square bracket? It's called coordination sphere, and outside the square bracket it's just compensating the charges, so that is called counter ion. Okay, and then how many ligands are attached with the central metal atom? That is our coordination number. Okay, these are the terms present in coordination complex chapter. Before diving into what is coordination compound and the double salt differences, I would like to give you a quick update which we have introduced. That is, you can ask the questions to me. It will get answered within 24 hours. You can ask n number of questions. I'll be attaching the link in the first comment or the description. It is a Ask Your Doubt portal. It is completely free. You need not to do anything. Just put your mail ID, upload your questions. It can be of 10 questions, 20 questions, 100 questions, because exam time is there. So people are very busy in solving questions. So why can't you do that? So solve the questions, mark down the doubts and send it to me. I'll give you the answers for all your doubts. Okay, that is a quick update. Let's get back to the topic. That is coordination compound and the double salt. What's the major difference between these two is that coordination compound may or may not be ionic. As I told you, outside the coordination sphere there is a counter ion which compensates the ions. So it can be of ion or the neutral compound. But in case of double salts, it is an ionic compound and does not contain any coordinate bond. It's an ionic, isn't it? Then the next difference is that coordination compound retains its identity in the solution form also. If I am dissolving the coordination compound by using water or any other solvent, it will get dissociated as this kind of ions like counter ion and then the complex, the coordination sphere part. But in case of double salt, it will get dissolved as its ions, like double salt loses its identity. Okay, these are the major differences. The question can be asked in the way, which of the following is a double salt? Which of the following is not a coordination compound? Okay, so the sphere will be there. For an easy way, sphere will be there in case of coordination compound. What are the types of ligands? The first one is unidentate. It binds to the metal. It binds to a metal through a one donor atom. Here you can see Nitrogen is a donor atom. Bromine is a donor atom. Cl is a donor atom. Only one way of forming the bond. But in case of bidentate, it binds through two donor atoms. For example, ethylene diamine. We write that as En. Oxalate C2O4 2-. Okay. So these are some bidentate ligands binds to two donor atoms. Polydentate means it binds to multiple donor atoms. The famous example is that EDTA. What is EDTA? Ethylene diamine tetraacetic acid or tetraacetate. Okay. It is having a hexadentate. 6 donor atoms are present in EDTA. Point to be noted. Note it down. EDTA is having a 6 donor atoms in it. The next one is chelate complex. The complex where the polydentate or bidentate ligands form a ring structure around the metal ion. Mostly these chelation, wherever the chelation happens, wherever the chelating ligands are there, that complex would be much more stable than others because it is forming a ring which makes it much more stable. Okay, ring formation is nothing but the chelation. The next type, that is ambidentate ligand, the most important part. Ligands that can bind through two different atoms, but one at a time. Okay, here let's take NO. Nitrogen can also donate, oxygen can also donate, but the donation happens from either of the side, not both at the same time. Okay, depend on which atom is donating, we will name it. Similarly, this example, SCN. Sulfur can also donate, nitrogen can also donate. So these are some ambidentate ligands. And you can take an example of NO2 also. The next part is the nomenclature of coordination complex. How we can name it. Like we saw the IUPAC name for organic compounds, here also we have separate rules. Coordination complexes are in the separate world like an organic chemistry. First rule is that cation should be named first, followed by the anion. Then cation means the ionic cation part, which is outside the complex. Our complex itself can be of cation. We'll see the examples, don't worry. Then non-ionic compounds are given a single name. There are certain ligands where the ligands must be named before the metal. Metal will be named at last. And then the neutral ligands are named as their molecular names except aqua, which is H2O, and amine, that is NH3. Anionic ligands end with O sound. Let's say I'm having Cl. It should end with chlorido, not chloride. Chlorido, bromido, iodo. Okay, fluorido. Then if cyanide means cyanido. So anionic ligand, which is out, anion means the part when we are separating the complex as positive and negative, which if the ligands are coming as an anion part, the counter ion is coming as an anion part, then that is anionic ligands. That should end with the O sound. And also prefixes. Di, tri, tetra are indicate the number of similar ligands. Okay, if more than 2 or ligands are there, 3 ligands are there, that should be named with the prefixes. Then the oxidation state of the metal is indicated in the Roman numerals. And finally, for the bridging ligands, the prefix is used is mu before the ligand's name. Okay. Let's see some examples of how to name the coordination complexes. The first one, that is K4FeCN6. Okay. The first rule, the cation part must be named first. Which is cation part over here? Don't go inside the coordination sphere. Just be outside and check which is anion and cation. Potassium, that is outside the coordination sphere. We know that metals, especially alkali and alkaline earth metals, always want to be in more electropositive, right? So if that is coming as a counter ion, obviously that is an positive part, that is cation. So potassium is our cation. So it starts with potassium. Then ligands. How many ligands are here? 6 ligands. So hexa. What is the ligand? It is Cn. Cyanide we usually use, but here we should name it as cyanido. Okay. Then what we have? Iron. That is ferrate. Or iron also you can mention. Ferrate. What is the oxidation state of metal ion over here? How we can find it out? So for that I am giving you the trick. This is 4 minus, isn't it? K plus and 4 minus. So metal oxidation state, I don't know. I am taking it as X. And cyanide. How many cyanides are there? 6 cyanides are there. So 6. That is a monodentate ligand. So minus 1. And then overall the charge is minus 4. So X becomes minus 4 plus 6, that is plus 2. So the oxidation state of iron is 2. Okay. Then we'll see one more example. Let's say this example, CO, that is cobalt, which is having the ligands nitro and amine. It is a neutral compound. So outside the coordination sphere we don't have any. So first we have to start with the ligands. So what are the ligands are present over here? Amine and nitro, right? So as per the alphabetical order, amine should come first. How many amines are there? Triamine. So triamine, and then how many nitro? Trinitro. Trinitro, and nitro, you could see, that is an ambidentate ligand. Either oxygen can donate or nitrogen can donate. See here it is mentioned NO2, which means that nitrogen is donating. What if oxygen is donating? Then they would write it as ONO. Okay. So to mention that in the name, I am taking N. N. What is the central metal atom? Cobalt. And find out the oxidation state, which is 3 for cobalt. Okay, so that is the name of this compound. I am giving you 2 more complexes. Try to find out the name. And if you can, just put it in the comment section. Let's see how many of you can solve. How many of you are ready to write the exam? So try to give the name for these 2 compounds. Let's move on to the theories for present in coordination complexes. The first theory is a very simple theory, Werner's coordination theory. There are 2 parts. He is saying there are 2 parts in the coordination complexes. That one is primary linkages, another one is secondary linkage. So if I am taking any coordination complex, the primary linkages are satisfied by the anions, contribute to the oxidation number and are ionizable. Say for example, if I am taking the complex of CO, CN6, Cl3. Okay. So in this case, which are satisfied by the anions and contribute to the oxidation number. So without this becomes 3+, isn't it? So, and these are ionizable. So which is, this is primary, and the secondary linkages are satisfied by the neutral or anionic species, which is ligands, contribute to the coordination number, which is coordination number, here the 6 is coordination number, and are non-ionizable. Inside the coordination sphere, that is non-ionizable, right? So here the secondary linkage is cyanide to cobalt. That's what they are saying in Werner's coordination theory. So don't get confused between these two. Primary, which is outside the coordination sphere, secondary, which is inside. Secondary is more of the ligands. Okay. The next most important part in this chapter is that isomerism in coordination complexes. There are two types of, the broadly classified types are structural isomerism and stereoisomerism. Right. We already done a video on, actually 2 videos on isomerism, isn't it? So now we are going to see structural isomerism in coordination compounds. The first one is ionization isomerism, where the different ions are produced in solution. Say for example, we know that when we are adding these complexes to water or any other solvent, it will produce ions like this. Correct? Sulfate and then its consecutive coordination sphere complex. So if that is changing, the ions present in outside the coordination sphere changes, then that is belongs to ionization isomerism. Okay. Then next one is hydrate isomerism, where the number of water molecules as the ligand changes. For example, here you can see CrH2O 5 times, outside the coordination sphere Cl is there. And in the second one, I am having 4 H2O inside the coordination sphere and 1 Cl. And outside the coordination sphere, I am having 1 Cl and 1 H2O. So number of water particles changes inside and outside the coordination sphere, that is hydrate isomerism. The next one, that is coordination isomerism. Where the ligands are interchanged between the cationic and anionic complexes. Say for example, here I am having the 2 complex, which one is cation, another one is anion. But the ligands are exchanged. So in that case, that is coordination isomerism. The ligands present in different coordination sphere is getting changed. The next one, that is linkage isomerism. That's what appears for the ambidentate ligands. Okay. Say for example, here you can see nitro, the N is participating in the coordinate bond. But in case of second one, that is nitrito, where oxygen is participating in the bond formation. So where the linkages of the ligand is changes, which is called linkage isomerism. Okay. Then the next type, that is stereoisomerism. Many questions can be asked from this part because it is bit confusing. We'll make it clear for you, and which is important also. The first part, that is geometrical isomerism. So what is geometrical isomerism? It occurs due to the spatial arrangement of the ligands, especially in square planar and octahedral complexes. The next isomerism is called stereoisomerism, where we are going to see geometrical and optical isomerism. But I'm going to hold this for now, because to understand these, we have to know the shape or the structure of the complexes. Okay, so for that, first we are going to see the structures, how we can derive it, and then we are coming back to the isomerism. To know about the structures, we should know some theories. The first theory, that is valence bond theory. Valence bond theory is given by Linus Pauling, and he is talking about hybridization and orbital overlap. Okay, so the first assumption of VBT is that a sufficient number of vacant orbitals must be available in the central metal atom for the bond formation. And the central metal ion can use the suitable hybridized orbitals like sp, sp2, sp3, dsp2 and dsp3 for the bonding. The number of orbitals used for the hybridization is equal to the coordination number of the metal. Okay ma'am, we know the assumption, but I don't know how to produce it, how to recreate it. Don't worry, we'll cover it with an example. It is very simple. First keep that in your mind. Okay, VBT is very simple. So let me take an example. Let me take a nickel Cl4 2- complex. Okay. What he is saying is that first they should have some accommodation facility. Let's calculate the oxidation number so that we will get to know how many electrons are there, isn't it? So nickel, what would be the oxidation number? X plus 4 chlorines are there. 4 into -1, which is equal to -2. So overall X becomes +2. Right? So nickel is in +2 oxidation state. So the electronic configuration becomes, after argon, 3d 8 4s2 in the ground state. Here we are having 3d8 4s0. Correct? So I am taking 3d8 4s0 and I am going to fill the electrons. Okay, I just filled those electrons. This is our 4p, 3d, 4s and 4p. Okay, now we have 4 chlorine atoms are approaching nickel. Each of those atoms will give 2 electrons to nickel to form the coordinate bond, right? So in that case, each of those Cl will come and attack s and p orbitals. So the hybridization becomes sp3, right? So sp3. So what is the shape of the or structure of the complex? sp3 means tetrahedron. Correct? So does it have any unpaired electrons? Yes, it is. So which makes it paramagnetic. What if they are asking the magnetic moment? Then we know mu s is equal to n into n plus 2. So two unpaired electrons are there. So overall, the magnetic moment becomes 4 into 2 root 8, right? Which will become 2 point something. Okay. So this is how you have to find it out using VBT. Let me take you through another example also for octahedral for a 6 ligand system. Mn CN6 4 minus. Okay. So here, what is the oxidation state? By the time you must be knowing how to calculate the oxidation state. Yes, that is plus 2. So Mn plus 2. 2 plus oxidation state. So what would be the electronic configuration? In ground state, Mn is 25. So 3d5, 4 is 2. Here it becomes 3d5, 4 is 0. So I'm drawing 3d, 4s and 4p as well. Okay. So 5 electrons in 3d and 0 electrons in 4s and 4p. Okay. So as Cn approaches Mn, what happens, Cn is a strong field ligand, but unfortunately, while they have proposed VBT, they didn't find that. So simply he was mentioning that MnCN6 is having a diamagnetic behavior. MnCN6 that is having the paramagnetic behavior, and the hybridization becomes D2sp3. Okay, but why that is happening like that? He didn't found. Later, there is a theory called CFT. He just ordered the ligands in certain order of strong field and weak field. Okay, so what that will do? Weak field and strong field ligands, what that will do? Weak field ligands won't pair up. It will remains as such. But in case of strong field ligand, it will pair up against the Hund's rule. These two things you have to remember. Okay, it is so strong, so it creates own rule. It goes against the Hund's rule of maximum multiplicity. Okay, it just pairs up. So how it gets pairs up, So here I am having 5 electrons. So at the excited level, because of the arrival of Cn, it becomes like this. Okay. Once it became like this, there is a 2 empty spaces where the Cn can occupy. Two empty spaces in 3D, 1 to 4s and 2 to 4p. 3 to 4p. Okay. So total 6 Cn. D2sp3. What would be the shape? For D2sp3, it is octahedral. More precisely, that becomes inner octahedral. Because if D2 comes first, then that is inner octahedral. If D2 goes next, then that becomes outer octahedral. Okay, so one thing you have to remember, weak field ligand, strong field ligand. Weak field ligand won't pair up, but strong field ligands get paired up. Okay, so I'm giving you few exercises. Just do it and let me know what is the hybridization and the structure. Okay, so the first one, nickel Cn 4 times 2 minus. For Cl we did that. For Cn, find it out. Cn is a strong field ligand. Then Cu copper NH3 4 times 2 plus. It is also getting paired up. Find it out, the hybridization and the structure of these through two complexes. Okay, these are the most important and frequently asked complexes. I am giving it to you. Okay, so we already discussed the magnetic behavior. If that is having a unpaired electrons, then that is paramagnetic. If that is not having unpaired electrons, then that is diamagnetic. Okay, also diamagnetic are low spin complexes and paramagnetic are high spin complexes. Fine. What are the limitations of VBT? As I told you, it fails to explain the quantitative interpretation of magnetic data. So how it is paramagnetic, how it is diamagnetic, he didn't find it out. And doesn't predict the color exhibited by the coordination compound and cannot explain the thermodynamic stability or kinetics of coordination compounds. It fails to differentiate between strong field and weak field ligands. These four are the important limitations of VBT. I just listed over here the hybridization and geometry of according to the VBT. Okay. Next, we are going into CFT. The next theory coming into picture, where he explains about weak field and strong field ligands. Okay. This is most important concept. The questions, lots of questions can be asked from this part. Okay. So the first thing, CFT means crystal field splitting. Splitting. The word splitting is there, which means there should be some kind of splitting. What kind of splitting will be there? Most of the hybridization happens in a d orbital. We are talking about the coordination complexes in d orbital. Right. So, the d orbital splitting is happening over here. We are having 5 directional paths in d orbital, right? Those are getting splitted. But how? There are 2 types of molecules, the complexes. The first one is octahedral complex. The second one we are going to see, that is tetrahedral complex. We are not going to cover square planar. They won't ask much questions on square planar. We will only concentrate on octahedral and tetrahedral, which is very simplest one, as I told for VBT. You also see that how simplest that is, right? So for octahedral complexes, the 5 d orbitals are split into T2G and EG. Okay, so T2G means where dxy, I am writing it in different color, dxy, yz, zx are there. Similarly, EG level, that is higher energy level than the low T2G, that is dx square minus y square and dz square. Those two are in the higher energy levels. So how the splitting will be, I am drawing it over here. So what happens in the ground state? The 5 are in the degenerate energy levels. So 3D upon it get excited. Okay, so it is getting splitted up to two parts, that is EG and T2G. Some of you asked this part, VBT and CFT in detail. That's why I'm explaining you in detail. If you're having any questions in any concept in chemistry, you can just comment over there in any video. Okay, just comment over there. By seeing that, we'll create a video for you. Okay, so EG and T2G. So as I told you, for T2G, that is dxy, dyz, dzx. And for EG, dx square minus y square, dz square is there. Okay. So distance between these two energy levels, we are taking that as the overall, that becomes delta O, that is del octahedral. Okay, or 10 dq. So mostly we'll stick with octahedral only. So from this point to the center point we call that as barycenter. So from this point to the center point, the value is plus 3/5 del octahedral, and from center point to the low energy level, that becomes minus 2/5 del octahedral. Okay. So 3/5 you can take it in decimal point also, 0.6, and then 2/5 you can take that as 0.4, but the values are same, 3/5 and 2/5. Okay. Let's see about tetrahedral complexes also. Tetrahedral, we have E and T2. We don't have G here because tetrahedral is not symmetric in nature, right? The structure is not symmetric. G refers to gerate, which is for symmetric objects only. So we are just mentioning it as EG and T, E and T2. Okay. E, which becomes a lower energy level now, and T2 becomes a higher energy level. But the d orbitals separation is just the same. X square minus y square, dz square are in E, and dxy, yz, zx are in T2. How we'll write this separation? From 3D, we are having T2 at the higher energy level and E in the low energy level. So dxy, yz, zx, dx square minus y square, dz square. Okay, so this is for tetrahedral and the another one for octahedral. Okay, so from VBT we know that which is tetrahedral, which is octahedral. But if they are having 4 ligands in total, okay, in total, then that is belongs to tetrahedral or octahedral, that we know that. And if that is having 6 ligands in total, that will belongs to octahedral. Tetrahedral and square planar for coordination number 4. Octahedral is for coordination number 6. Okay, let's move on to how to do these problems. For that, we have to know about the spectrochemical series, isn't it? So spectrochemical series is nothing but the order of how the ligands are reacting. So I'm giving you the order, which is I minus, Br minus, these are the important ligands, SCl minus, Cl minus, F minus, N3 minus, OH minus, H2O, EDTA, NH3, En, NO2 minus and Cn minus. So we start with the weak field, ends to strong field ligand. So how we can memorize it, ma'am? So there is a simple mnemonic to memorize the spectrochemical series. We know that this series is very important for solving CFT, right? So for that, I brought some clowns from Narnia over Easter every night coming Christmas. So as you know, I stands for iodine, Br for bromine, S for some, which refers to SCN minus, Cl clowns from fluorine, F minus, Narnia, N3 over OH, Easter for EDTA and En, night for nitro and C for cyano. So aqua, that is H2O, come between over and Easter. You can remember it like over aqua Easter. Cool? So this is the mnemonic you can remember. If you are having own mnemonic, that is also fine. I brought some clowns from Narnia over aqua Easter every night coming Christmas. Hope this is useful to you. Let's get started with solving tetrahedral and octahedral related examples. The first one I'm taking out here, that is octahedral complexes. I'm taking two type of ligands, okay, strong field and weak field. Let me take Fe H2O 6 2 plus and Fe Cn 6 times 4 minus. In both the state you can see the oxidation number is 2 plus, right? So the number of electrons are same, but what happens to the in the presence of strong field and weak field ligands, that we are going to see. So I'm drawing diagram for strong field and weak field ligands. It starts with 3D, Eg, T2G. And once again here Eg and T2G. So tell me how many electrons will be there in Fe2 plus 3D6? 4 is 0, isn't it? So 3D6, 4 is 0. 6 electrons I should distribute it throughout Eg and T2G. In case of weak field ligand, in the presence of weak field ligand, what will happen? We saw that in BBT also. It will not undergo any pair up. So first 3 electrons will fill over here. Then next 2 electrons go up. Another 1 electron will go down. That is what happened in weak field. It will not do any para. That's what we saw in the VBT. Similarly, here according to the CFT, in case of weak field, it will fill T2G for the half fill, and then it goes to EG half fill. If that is there remaining, then comes to the lower energy level. But in case of strong field, all 6 electrons are getting filled over there in the T2G itself. Okay, so this is what happens. So T2G 4, EG 2, and T2G 6, EG 0. So this kind of questions can also be asked, and also you have to know about stabilization energy, crystal field stabilization energy, that is CFSE value. I told you, right, from barycenter what is the value for EG and T2G. So we are going to apply that over here. So from barycenter 6.6 del octahedral, and here 0.4 del octahedral, isn't it? So we are just going to find out the CFSE using that. So minus 0.4 X belongs to how many electrons are there, plus 0.6 Y into del octahedral. That is the formula. So how we can find it out? Minus 4.4. How many electrons are there? 4 electrons into 4 plus 0.6. How many electrons are there in EG? That is into 2. So overall it becomes minus 1.6 plus 1.2. So this is 0.4 minus 0.4 del octahedral. So these values can be asked as a question. Let's find it out for strong field ligand also. The CFSE becomes, here I am having minus 0.4, isn't it? So minus 0.4, X is only there, Y part we don't have electrons. So I'm just going to put 0.4 into 6, which becomes minus 3.0 del octahedral, which becomes 2.4 del octahedral. Okay. So what is the importance of having it? If del octahedral values are more or high, what it affects? If del octahedral value is more than pairing energy, then the electrons will remain unpaired and forms a high spin complexes. And if that is opposite, then it forms low spin complexes. Okay. Strong field ligand, it will get paired up in that way also you can answer to these questions. Similarly, you can work on the tetrahedral part. Similarly, you can work on the tetrahedral part where I am giving you the values. It's like plus 0.4 del octahedral and minus 0.6 del octahedral. Okay. Plus indicates the higher energy level, minus indicates the energy is getting lowered. Okay. We are going to see the relation between del octahedral and tetrahedral. Sometimes the questions can be asked using this formula, that is del tetrahedral, which is equal to 4 by 9 del octahedral. Okay, so this thing you have to remember. So 4 by 9 of del octahedral. Sometimes they will give you the tetrahedral value, ask you to find the octahedral value. Okay, so as I told you, after finishing the structures, we are going to see the isomerism part. Okay, so the first isomerism, that is geometrical isomerism. The questions can be asked by giving the types and asking for which can exhibit geometrical isomerism, which cannot. Geometrical isomerism, we very well know, that is occurs due to the different spatial arrangement of the ligands in square planar and octahedral complexes. It is not for tetrahedral because it is not symmetrical in nature. So first we are taking square planar complexes. Square planar, where I am having A to B2 type. There are two ligands, one ligand, both are monodentate ligand or unidentate ligand, and total I am having 4. Each one is donating 2 electrons each. So here it can show cis isomer and trans isomer. What is cis and trans? If that is present on the same side, then that is cis. If that is present in the opposite side, then that would be trans. So I am taking platinum amine complex. So both the ligands are present on the same side. Then this is cis. If that is present on the opposite side, then this becomes trans. Right. So this is a very important isomer because cis isomer is having different character than the trans. This complex is called cisplatin, which is used very much in medicinal field. So it used in a cure for cancer. But trans isomer won't exhibit those properties. It is biologically inactive. Geometrical isomerism in square planar complexes is observed when two different types of monodentate ligands are present. Okay. Now we are moving to the octahedral complexes. Octahedral complexes where the cis and trans can exhibit. In case of MA4B2 and MA3B3, in these type, this can show isomerism, geometrical isomerism. Particularly this guy A3B3 show FAC and MER isomer. Say for example, I'm having cobalt, which is having amine ligand. Along with that, I'm having NO2, let's say. So this is a octahedral arrangement. Either it can represent it like this, or can either represent it like this or like this, where NO2 and another NO2 is present over here, and remaining are amine. Can you find the differences between these two? Where I'm having NO2 is forming a triad, right? But here it is not possible. These three NO2s are forming a triangle. There is a difference between these two isomers. The first one, which is called facial or FAC isomer. The second one, where NO2 is present in the equatorial only, that is our mer isomer, meridional or mer isomer. Okay, this is the most important type of isomer because it is different, no? So questions can be asked a lot. The another type, A4, B2. If B2 present on the same side, then that is cis. B2 present on the opposite side, then that belongs to trans. Then the next type would be MAA2 B2, or it can be of MAA2 BC. Okay. So in this case also cis and trans form can exhibit. AA I am referring to a bidentate ligand. Okay, if the bidentate ligands on the same side, then that would be cis. If that is on the opposite side, then that belongs to trans. Okay. But in case of optical isomerism means the isomers which rotate the plane of polarized light. This occurs only in octahedral complexes. It occurs only in octahedral complexes where, especially with the bidentate ligands. Okay, so for example, MAA3. For that, you can take cobalt with En tries 3 plus. It is a octahedral complex which exhibit optical isomerism. If that is rotating clockwise, then it is D isomer. If that is rotating on the anti-clockwise, then that would be L isomer. And the mirror images can't be superimposed. And another type that would be MA2 B2. In that case, I would like to tell you an example of COEN twice Cl2. It can also exhibit optical isomerism. There is another isomerism that can exhibit, that is, if all the ligands are different, that is kind of A, B, C, D type in square planar. This can give up to 3 isomers. That's it about the isomerism part. Then we are moving on to the metal carbonyls. Metal carbonyls are nothing but metal is attached with the CO ligand, carbon monoxide kind. CO ligand. Metal carbon bond in metal carbonyls as sigma and pi character. Sigma bond, which the ligand donates a lone pair from carbon to metal's empty d orbital, and the pi back bonding happens. Pi bond happens when the metal donates the electron back to ligand empty orbital. Say for example, I am drawing this, that just formed a bond with the donation from the carbonyl, right? Once it is formed, the metal is having some electrons, right? And the ligand that will have some empty orbitals. So from here it is donating the electrons, kind of a written gift. What is the use of this type of bonds? It gives extra stability. Whenever the extra bond happens, but that will give you the extra stability to the complex. So metal is giving the electrons to vacant anti-bonding orbital of the carbonyl ligand. Okay, this effect is also called synergic effect. It is the characteristic property of back bonding that stabilizes or strengthens the metal ligand interaction. Okay. So that's it about the coordination complexes. Now we are moving on to let's solve some questions based on this chapter. The first question, which is asked in JEE Advanced 2018, which of the following coordination compounds can exhibit geometrical isomerism? I told you it is only suitable for square planar and octahedral. So square planar also M A2B2 type, and octahedral M A4B2, and in case of, I'm talking about the monodentate ligands, M A3B3, right? So here you can see all are monodentate, so that's why I have told you, and which is similar to this. NH34Cl2 and NH36. No, this is not an answer. And what about this? This is also not. And what about A5B? That is also not possible, because same ligand should be on the opposite side. That's what we are meaning for the geometrical isomerism. So answer to this question is option A. This question is asked in JEE Advanced 2016. One of those toughest questions. Let's see how tough is this. The number of optically active isomers possible for COEN 3 times 3 plus. This complex has 3 bidentate ethylene diamine ligands, right? So there is no, it is an octahedral structure, and let me draw the structure also. So it is an octahedral geometry, and there is no plane of symmetry for this structure, isn't it? Usually in octahedral we do experience some plane of symmetry, but here, since all are bidentate ligand, we don't have any plane of symmetry. So it exists as 2 non-superimposable mirror images. One is D isomer, another one is L isomer. So answer to this question is 2. This question asked in JEE Main 2021, which of the following complexes exhibit both optical and geometrical isomerism? So let's see these compounds, which is, first one is A4B2 type, second one is AA2B2 type, and the third one, that is A6 type, and the fourth one, that is A4 type. Obviously C and D can't exhibit any isomerism, right? So what about A and B? AA2Cl2 and A4B2. A4B2 and B, can it exhibit optical and geometrical isomerism both? This you can see, this can exhibit cis and transform. And what about optical? Yes, it can. So that's why we have seen in the video also, in the detailed video also, it can show D and L isomer. So answer to this question is B. What about A? It shows only geometrical, not optical. So this is not our answer. Then this question, which among the following will show linkage isomerism? Linkage means amphoteric ligand should be there. Where the amphoteric ligands are there? Only in option A. So NO2 can donate the electrons from N also or from oxygen. NO2 or ONO. So whenever the linkage isomerism comes, check for ambidentate ligands and put your correct answer. Then this question asked in 2022, which of the following is an example of an optically active complex? I told you so many questions can be asked from isomerism part. So let's see this. This is AA 3 type and this is A6 type. This is A4 type and last one is also A6 type. Which of the following is an example of optically active? Obviously, the answer to this question is option A. People who were commented as option A, then you are correct. What about these three answers? These three options? These have symmetric ligand arrangement, so they are optically inactive. But in case of En, that is not having any symmetry. So answer to this question is option A. Which of the following complexes does not exhibit geometrical isomerism? The first one, which is A2 B2 type, second one A4 B2 type, and the third one A4, and the fourth one is also A4. They are asking does not. So either from these two only the answer should be. Both are A4, but we know only the square planar complexes will show the geometrical isomerism, not tetrahedral, right? Among these two, which is tetrahedral, which is octahedral? So D, which is tetrahedral, and C, that is square planar, correct? So tetrahedral complexes do not exhibit geometrical isomerism, which makes option D is the correct answer to this question. If you want to know more about how to solve, just go above and see the solving part. And this question, most difficult JEE advanced question ever asked. A complex of iron has the formula iron with acetate. The number of optical isomerism possible for this complex. This is a bidentate ligand. Fe with AA type. Right. So how many optically active isomers are possible? Similar question we have solved before. The structure will look like this, where it will have no plane of symmetry. So only two isomers, that is D and L isomer, possible for this complex. So solve as many as questions you can. We have just updated previous year question papers according to your wishes and your examinations. I'm just posting the link over here. Just click it and attempt those questions. Practice yourself. Solution is also present over there. And if you're having any doubt, click on the Ask Your Doubt portal and send your doubts to me. It can be of hundreds of questions. I'll dare for you to answer. So make use of it and practice more questions. Thank you.